Okay, I'm now live. Let me just update my banner here. So this is earlier than I was going to go online. I was going to go online at 2, but you know what? Had lunch, finished the work that I needed to do today, and I figured, you know what? I'd rather get started with this rather than sit around and do nothing for half an hour waiting for the time to officially start. Besides, I'm not imagining that there's going to be too many people who are like waiting for the 2 p.m. start time to watch me learn quantum mechanics. So this is probably for the people who are maybe watching it long time after, or they're just skimming it, or they're just, want to know that I was actually doing it. And they're just interested in what methods I was looking at or highlighted the technique. So with that in mind, where are we? So this is a good opportunity, since I'm on a little early, to recap what we've covered so far, where we're at. So I mentioned that sort of my goal over the last couple of days was to get to lecture 10. And the reason for lecture 10, and let me just get the, this, you know what, I'm going to open a new window here. And I'm going to open up the, all right, I'm going to open up the calendar here. So 1 second. Let's add the screen share. And let's bump down the, okay. And set into live. Okay, so I've just updated it so that now we can look at the calendar. Just open a new window. So why did I want to get to 10? So this is, first of all, the first junction before exam 1. So it's an important kind of milestone in the course for that. Second, it's half of the problem sets were due before this time. So this was kind of, even though it's not halfway mark in terms of the actual lectures, because we have 24 lectures and I'm only up on lecture 10. This is 50% of the problem sets were due at this point. And I figured this was going to be enough depth into it so that I'm not getting, really when you're learning anything, I guess I'll explain it this way. When you're learning anything, there is an amount of depth. You can just keep going deeper and deeper and deeper. So one example, I'll give an example of why I choose this approach and what kind of error I might have made if I had decided to, just spend an even amount of time with each lecture. So in the beginning, there were a few concepts that, let's say, that were from previous classes that I didn't have, let's say, a mastery over. So one of them was complex conjugate. And now I feel like I know what the complex conjugate is, but there's more depth than that. I could try to come up with intuitive pictures of the complex conjugate. I could try to come up with an analogy of it. I could try to form the geometric description in my mind. I could go a lot of work. I could spend a month just talking about the complex conjugate. And the problem is that in terms of material of this course, I actually understand the complex conjugate pretty well. I was able to actually solve quite a few problems that involved the complex conjugate. So even though I don't have a perfect, mathematician level understanding of the complex conjugate, I have a good enough intuition, good enough understanding to be able to do a lot of things with it. Now, compare that to some of the stuff that we did in lectures. I believe it was 9. I want to say 9 was this. Yeah, 9 and 8, where we did the brute force method for solving the partial differential equations of the time evolution of the Schrodinger equation, as well as using these raising and lowering operators as a way of solving particular bound states of the Schrodinger equation. These are things that I actually, even listening in the class, I didn't fully understand everything that was being said or what was motivating certain actions or certain decisions or why they were doing this as opposed to something else. So if I were to describe my level of confidence in things, my level of confidence in complex conjugates is here versus my understanding that material's there. Now, if the complex conjugate came up in lecture, maybe 2 or something like that, and I was evenly spacing out, I might have spent, I could have spent a whole day just thinking about the complex conjugate. And then when I get to doing this part that I don't understand, now I have a lot less time to work on that. So the reason to go through more of the lectures rather than just doing them exactly the calendar suggested by MIT, rather than doing them, let's say, okay, well, after after lecture 2, I did problem set 1, and then after lecture 4, I did problem set 2. The reason to not do that is because I don't actually know what the difficulty is going to be for me in these, and doing in this pace was pretty good. Now, if you have more time, so that running out of time is less of an issue. So if I were doing this over a typical semester, I'm doing only one class over 1 month, whereas an MIT student would probably do maybe 4 or 5 classes over 1 semester. So I'm not too far off from an MIT student here in terms of my schedule. But again, if I had just lots of time, so maybe I'm only doing this 1 class and I'm just taking my time, I'm not trying to prioritize anything, then there's nothing really wrong with doing it in this calendar approach. And there's nothing wrong with that. But I like to do it this way just because I get a little bit forward. Now, the disadvantage of doing them clumped up is that you can have misunderstandings and confusions that don't get clarified or don't get put to the test before you actually get a chance to do those problem sets. So you can get into higher lectures where you think you get it, but you really don't because you never learned the basics. So there's a bit of a trade-off point. And for this particular class, getting to lecture 10 was kind of my goal because I could chew through enough of the problem sets, but I wouldn't get so deep into it without having any practice that I didn't have any of that feedback or test of my knowledge. Now, to be fair, there were these kind of clicker questions in the class. So the last lecture I did was kind of like a live in-class quiz. Where there were 16 different questions, and I got most of those right. So that's already some feedback on my understanding. In other places, when he's about to do some kind of formula or questions, I am already doing it. I'm already going through this. Just before I get started with here, Neil has a question for any advice for medical students. If you're studying medicine, if you Google, I think it's an evidence-based guide for studying medicine. There's an ebook that I read. It was recommended to me by someone. It's really good for an overall studying approach for studying medicine specifically. So I won't be talking about too many off-topic things, but since this has been asked before, that would be my response, is to Google for that guide. So in terms of where we are right now, it's now time to move into the problem sets. And I really see basically there's kind of 3 layers to doing a class like this, a quantitative class. The first layer is just watching the lectures or, reading the textbook. The textbook, I'm not going to probably use too much for this class because there are tons of resources. It's mostly just doing the work. But for some classes, I did the MIT challenge, for instance, there were no lectures, so I had to use the textbook. So there doesn't really matter. Textbook versus lecture is not a huge difference. Sometimes it's nicer to watch lectures. Sometimes it's nicer to read a textbook. It doesn't really matter. But the main thing is that you are covering the material. So I call this coverage. And then the second layer is doing actual practice problems. And so for a quantitative class, for a programming class, for any class where you're going to be asked to solve problems, not just merely regurgitate facts, you need to actually see some problems and work on some problems. Now, this isn't available in every single class you're going to learn, so sometimes you have to create your own problems. You have to invent your own things to do. But the problems give you a rough sense of how deep do I need to know these things for the purposes that my professors expect of me? How deep do I have to know this to pass the exam? I'm not saying passing exams is the end goal of a self-education project like this, but it's a reasonably good proxy for did you understand things. If you can pass an MIT OpenCourseWare exam, you probably understood it somewhat. You probably didn't just memorize things because these are hard exams. So this would be the practice problems. And sometimes these 2 layers are enough. Indeed, for a lot of the information you cover, these 2 layers are going to give you enough coverage. But I like to think of a 3rd level, which I'm going to call insight, which is doing things like the Feynman technique, forming analogies, creating diagrams, trying to explain it to other people as if you're explaining it, or trying to explain it to yourself as if you're explaining it to other people. This deepening of understanding, and I particularly apply this to core concepts, so things that turn up again and again and again, you want to have a deep intuition of them. That would be A. And B, I also apply it for very difficult concepts. So in terms of stuff we've covered so far, I would be very interested in maybe applying this Feynman technique to things like the superposition principle, which I already understand, but it'd be really good to get that really locked down intuition about it. Things like orthonormal bases for the eigenfunctions. This is something that I kind of understand, but I would really like to have an intuition about. in terms of things that I found really difficult, if I'm going to actually understand that the brute force method for doing the partial differential equation, or like all the logical thinking that got us to get to these raising lowering operators, I'm probably going to have to do the same thing. So it just serves sort of a dual role. So we've done the lectures. I have now completed these lectures, so we're probably not going to be doing any lectures for the rest of this week. People are saying, oh, the sound's broken. Yep, you are correct. Looks like I've got two microphones going at the same time. Thank you for helping me out with that. Let me just see. That was my bad. I switched the window, and when I added the window here, it decided to add another microphone in my little display. So hopefully if I go back to here, it'll just have the one microphone. Yes, thank you. All right. So now we're going to go over to the problem sets. I'm probably not going to do them just like question one, master it, question two. Probably what I'm going to do is I'm going to go through them, work on them a little bit, and if some of them are sticky, like I'm getting stuck, I'm just going to put a bookmark in them and come back to them. So working on the hardest problems is usually the right way of doing it, but because I'm going to do all the problems in these problem sets, like I'm not going to miss any of them. Getting that coverage is going to be good, because it's good to sort of like figure out, okay, what do I know? And then what are the things that need to be cleared up? Because sometimes you can get tripped up on a first question or a second question. So let's go over here, and actually, do I want to? I think I need to. Oh, I also want to display the problem somewhere. So let me add a little thing to this window here. 1 second. I'm going to make a new viewing for this here. So let's get our notes. Let's get me. And hold on a second. I want to switch the microphone so that we don't have that issue. And what else do I want to add? I want to add a screen share of the problem set. So let's add that here. So let's okay. So I should be able to do this like this. I don't know whether this is going to be readable. It's a little hard for me to see, but we can just see how it goes. If you're having trouble reading this problem set, all these materials are on the 2013 spring MIT thing. I am going to put them up there just so that you can see what I'm working off of, because I'm not going to print them out. I'm just going to do them on here. But if you're having difficulty, go to that course and you can see them all. This is all just material from their website. So let us go here and let's work on the problem sets. So I'm going to do these problem sets with pencil. I'm also a little nervous about how that's going to appear on the live stream. I think that doing it with pen is going to cause me a lot of headaches, as I accidentally write typos and then I'm scribbling out equations and stuff. So do I have a dark enough pencil that it will be visible here? So we'll try normal HB. I do have some artist pencils that are softer, which should also be darker in case this is not good. But I don't usually do it with a pen. This has been a new thing that I've been trying to do for visibility on the live stream. But pen is good for taking notes, but for doing algebra problems, it's just going to be a nightmare. All right. So this is problem set 1. So let's go with this first question here. So if we look at the problem here, I'm going to read it out. The radiative collapse of a classical atom. So this is the question that I'm kind of doing, but I didn't really learn anything new in the last 10 lectures for solving this one because it's probably based on the class that I didn't take, 803 waves. You know, you can see right here, it says we know from 803. So this is 804. I did 801 and 802. I did not do 803. But let's try our best. I don't think there's too many questions like this, so even if I get this one wrong, it's probably not going to impact my understanding of quantum mechanics too much. Suppose the world was actually governed by classical mechanics. In such a classical universe, we might try to build a hydrogen atom by placing an electron in a circular orbit around a photon. However, we know from 803 that a non-relativistic accelerating electric charge radiates energy at a rate given by the Larmor formula. So let's write this formula out. It is the change in energy over time is equal to negative 2/3 q squared a squared over c cubed. So what are these? Q is the charge on the electron. This is a convention I'm pretty sure I remember appropriately from 802. So this is the charge. This A, I'm assuming, is the length. Oh, yeah, no, sorry. I should just read the next thing. Q is the electric charge, and A is the magnitude of the acceleration. So this is acceleration magnitude. So magnitude meaning that it is a number, not a vector. And then C is the speed of light. So this is this change in energy. So question 1A, show that the energy lost per revolution is small compared to the electron's kinetic energy. Hence, it is an excellent approximation. To regard the orbit as circular at any instant, even though the electron eventually spirals into the proton. So basically, let's just start with a diagram. I like to start with diagrams because they kind of help make sense of it, and then you at least know what you're trying to do with the math. So we've got our positive core. I could probably draw this one with a pen because I'm not going to be doing a lot of errors with this. So we've got our positive core, and in this sort of fake model of the atom, we've got an electron going around it at some, fantastic velocity here. Now, we know that it's going to be losing through radiating off electromagnetic waves. We know that it's going to be shooting off these photons. It's going to be losing energy. Now, the first question is saying that, well, basically we want to assume that it's like we don't want it to be spiraling in like if it was like this, then the direction of it's not mostly circular. That's going to make it harder to calculate. So the first step is just saying that this that the energy loss per revolution is small compared to the electron's kinetic energy. So how big is the kinetic energy of this electron? So how can we figure that out? Well, how fast is the electron going? How do we know that? I think the idea here is that this formula is going to show that the acceleration, the energy lost here. This is dE dt is the kind of change in kinetic energy of this photon. It's going down and down and down and down this this well because it's radiating off light. But how do we compare this to the kinetic energy? So how do we know what the kinetic energy is of the electron here? think we need to know what these quantities are, right? We need to know what the typical electron mass is, what the how fast it's going. Is the way that this problem is supposed to be solved, do you think it's that we start like kind of imagining that there's this circular orbit, that it's moving in this circular orbit and that it's not radiating electricity at this point? I guess we know for a fact though that there's going to be this Coulomb force on the electron that's going to be going in. So it's going to be experiencing a force inward like this. And this is going to be define basically the acceleration that it's experiencing. And so I guess we're trying to say is that at the speed that it needs to maintain to be a circular orbit, this acceleration, so basically like the orbital velocity of the electron, that it is this orbital velocity. This orbital velocity is corresponds to a kinetic energy, which is much greater than this sort of dE dt sort of integrated over one revolution. This is what we're trying to say. Do we need some constants? It might be that these constants cancel out. So I might not need to look up the actual numbers. So let's say that QE is equal to the charge on the electron. So ME is going to be the mass of the electron. And then we need to figure out what its kind of stable orbital velocity is. I think the reason that we don't need to know because we'll notice sometimes you can also figure out questions by kind of what information they don't give you. So one of the things that is not in here is the at least in part A right now, is this radius here, which the speed is obviously going to be, when it's much further out, it's going to be going a lot slower, kind of same as a planet, right? Like Pluto goes a lot slower than Mercury does because the force is experiencing is a lot less. But I think that in the same note, if the electron were much further away and it were rotating, it would be accelerating more slowly. Because it's accelerating less, its energy loss is less. So I think these are also going to cancel out. I think the mass of the electron is also going to cancel out because we're dealing with the acceleration and the force is acting on the force is acting on the mass, but we're looking at the acceleration here. So, so I think, if I remember correctly, the Coulomb force, if I can spell Coulomb force right. If I don't know this, I'm just going to look it up. I have my textbooks from Coulomb Force. So there's a U there. I'm not sure. So this is something, it's proportional to charge of one, charge of the other, divided by the distance squared, I'm pretty sure, to some constant. something like this. You know what? Let's just look that up. Let's just look up the Coulomb Force, because I'm going to feel silly if I start getting things wrong at this stage. All right. So I have, this is the textbook that I used in the MIT challenge for 802 Ohanian physics. Love this textbook. So let's see if we can find the Coulomb Force here. Coulomb Force. You know what? I'm not seeing it there, so I'm just going to go into and find momentum. Go back to, let's just go find the electromagnets magnetism section, because that's going to be right in the beginning of that. The electric field. So this is, oh, it is with the U. So this is 573. All right. Do we have a formula here? So it's basically what I said here, that our Coulomb force is Coulomb's law of the magnitude of the electric force on a particle is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. So it's this constant. This is the charge on a proton, so this is good to know just anyways. And then this is Coulomb's constant. So, for historical ratings, it's usually written as this. So Coulomb's law, I was looking for Coulomb force. Coulomb's law is this. So I'm going to just ignore this kind of constant end right here, but basically we've got this, the right idea is equal to 1 over 4 pi E0. This is the force that it's experiencing. I guess I should say it should be in the direction of the radius. And I'll just make this a vector. So we're experiencing this force. Do I need the charge on the electron? I don't know, because we're using it here too. And I know that the electron, this is hydrogen atom. We know that it has one positive charge, one negative charge. So these two are the same. So I think I can just substitute this Q1, Q2, just making it Q squared here. All right. Now, where are we here? Let's see. This is our Coulomb force. Now we need to know what the force is for the for how fast it's going. Now the problem here is that the particle is going to be going slower further out and faster further in, but it's proportional to this. So I'm wondering whether, like, obviously I can just kind of plot this out for some kind of hypothetical A, some hypothetical radius A, and figure it out and try to cancel it. I shouldn't use A because we're using A for the acceleration. So let's just call this, let's call this D, because I've already used that in that equation there. So this is D. What do I want to do here? Loss per revolution. So we know we're getting pulled in at that acceleration. So this is the A. So if I put in this equation here, we know that it is this. This is the force. Now the force is, because we know from F equals ma, there's a mass term here. So the acceleration vector here, so if we want the acceleration vector, we have to divide out a mass. Q squared 1 over do I want to plop this into there? Because that's how much we're accelerating. Don't know D right now. I mean, M is a fundamental constant, so I suppose I could look it up. It's going to be in this book somewhere here, but I have a feeling I'd rather not, because I feel like they probably would have put it in there if I needed it. What do I feel? See, this question here is challenging for me, because we're dealing with, I'm kind of filling in some gaps. I never learned this equation, never learned this in 803. So I'm hoping the other problems are not going to be quite as mysterious to me right now. But I'm going to try to keep putting some effort on this problem, and then if I get stuck, I'll move back to it. So even though there's a probably pretty simple solution that I'm missing here, I'm going to start with that here. All right. Let me just put this book over here just so that I can get it out of the way. Running out of space here. Put our quantum mechanics book up there. Okay. So, I might want to find, let's figure out what the equation is for the orbital velocity. Let's get that in this picture, because I think that's going to be relevant too. So let's see if, I wasn't having that much luck looking at the index before, but let's try that here. Let's see if they have orbital velocity. Orbital magnetic moment, orbital period, geostationary. Circular C, circular, it's 226. Let's just take a look here. 226. This is energy for the orbit. Oh, for a circular orbit, the orbital speed is, okay, so this is gravitational, but we can just adapt it. Let me just get pencil here, okay. So let me just put a little bookmark here for where we were on the electrical page. So I'm just gonna show it right here, but I'm gonna be copying it down. So what we have here is V is equal to the square root of G ms over R. Ms is, I'm assuming, the mass of where are we getting ms? Is ms the mass of the sun in this? Or? Yeah, I want to say it depends only on the mass of the central object. Maybe that's not true. Equation 12. Let's go back here. Equation. Equation 12. Oh, okay. So ms is the mass of the sun. I'm looking here at circular orbits. So this is essentially our same thing for our Coulomb potential, but in gravitational. And so some people are saying centripetal force is provided by the Coulomb force. Well, we know what the force is. I'm just trying to figure out what we want for velocity for it to be circular. Perhaps that's in there and I'm missing it, but oops, where was I? V equals this. So I think if we were doing this with the electron, so if this is for the mass here, it's going to be equal to this square root over 1/4 pi e. You know what? I have to check because when we're deriving this, mv squared, yeah, it's acceleration. Here, let me put a little bookmark here. V equals Q. I've got some helpers in the chat here. Therefore, V equals Q over mr, square root of mr. So maybe I'm just not seeing it right now. I think, Let me just erase this for right now. Let's just put this over here. I've got some bookmarks if I need to go back to those pages, though. So what would I be struggling with here is that I am trying to figure out the velocity so that this has some circular orbit, because we need to start with some kind of kinetic energy. Like, we're not just in some system where these things are stationary and it just falls straight to it. We're at some kind of orbital velocity. So I need to figure out, I need to relate the this sort of Coulomb force to whatever the orbital velocity is. And I forget how to calculate the orbital velocity of the electron so that it would, minus this radiative force, so that it would stay on that circular track. So I'm going to just state that a little bit more clearly, what I'm missing, so that when I come back to this, I'll know what to look for. All right, so I'm just going to leave this for right now. As I said, this PSET 1 I think is going to be the hard one because it's dealing with some stuff that, again, either was, 8 years ago that I was doing problems. So if I did do a problem that involved some of this, I don't remember doing this in 802, but if I did one like this, again, it was about 8 years ago that I did it. And if it was in 803, then I didn't do it at all. So there is a chance that I'm missing something here that I just never studied. And so this is going to make this very difficult to solve. But I'm going to leave it for right now. And I'm just going to leave this with some space right here for number 1. I'm not going to leave a bunch of blank pages just because I'm going to go back to it later. But I think I have some handle of at least what I'm missing right now in the problem. So I think I'm going to skip past question 1 right now and recognize that I didn't finish it and go on to question 2. And we'll circle back. So thanks. I will keep in mind your suggestions of what I should do. So one of the readers has written down that I should include Centripetal Force. MV squared over R is equal to the force. I'll keep this in mind. So I'm not trying to dismiss any of your helpful points, but it's also important for me to understand where I'm getting things. And so not to mention that I'm trying to showcase how this process would work, even if I didn't have help from people watching who know more than I do. So let's do number 2, dimensional analysis. Okay, good. Some dimensional analysis, the thing that I was screwing up in all the classes when I was taking my pause breaks. So we're from one onto the other. All right, 2A, gravitational balancing. Consider a particle sitting on a table which is kept from floating away only by the force of gravity. The system is characterized by just 3 physical parameters: the mass of the particle, acceleration of gravity on Earth, g, and Planck's constant, 1 over 2 pi, or h bar is 1 over 2 pi h. The energy is given by E equals, okay, kinetic energy plus potential energy. All right, so let's, using only dimensional analysis, find the product of the powers mg and h bar, which give a characteristic energy E, i.e. you can write E is some some relationship of these mg and h, solve for A, B, and H. Can you find such a characteristic energy without using the Planck constant? All right, well, let's start with this energy formula then. So E is equal to this 1/2 mv squared. And this is, what is x? X is, I guess, the height. So these we already have. We already have these ones. So it's V and X that we don't have. So V is meters per second, and X is meters. So this is the dimensions of this. And our these are units. I'm trying to think of, like, he was saying units versus dimensions, so I don't want to use units. Maybe I should write these down differently. Maybe I should write this down as instead of, because I've also got the m there, which is mass, which is going to be confusing if I'm also using it for meters. So this is a length divided by time squared, and this is a length. And what I have is I have a length, oh, sorry, this is a length divided by time. Sorry, oops. And then what I have is a length divided by time squared. And I have a mass. And I have this Planck's constant. And what are the units of Planck's constant? Do I remember what the units of Planck's constant were? The dimensions of Planck's constant. I gotta stop saying units. Let me look back at my notes because I do remember writing that down. way at the beginning. Do I mention it here? Planck's constant. You know, I think I'm just going to look it up because otherwise I'm going to be here looking through my notes for a while. In this book. Planck's constant is related as joule seconds. So H is equal to, so let's go energy. It's energy time. Okay. Energy times time. All right, so we've got units of energy times time there. Oh, thank you, Mr. Kafka. You're one step ahead of me here. So we've got energy times time. So now how should we do the dimensional analysis to figure out what our kind of approximate measure is going to be? So this is an energy. So energy times time. This is length. This is a, sorry, this is a, let me just write these down. This one here, we have mass. And this one here, we have mass. And we have G, which we already figured out was length over T squared. So if we have these dimensions, that means we've got order M should be 1. So if I'm getting this right, alpha for M is going to be 1. It should be on order 1 because we just got one mass term unless we're adding it somewhere else. This is length times time, and this is length squared time squared. So are we trying to solve the problem by energy should be roughly equal to length time? This is energy time. What should we do here? So this, I'm just going to replace this with L squared. Let's clean this up a little bit. So I guess what I don't understand right now is that we've got two different terms that are being added together. And we're supposed to find just sort of a characteristic energy for the overall equation. Now, my guess is that if this is to be all multiplied together in one thing, that that we're looking at. Oh, you know what? Velocity squared. Geez, this is, yeah, there we go. Velocity. This was squared. I put length times time. It's length squared times squared. This is length squared times squared. So if it's length squared times squared, and we have these quantities, well, we know that it's going to be, okay, so this is going to be m. So we know it's going to be m. Hold on a sec. M else. So we know that it's going to be m L squared t to the minus 2. But we want to find it in terms of these constants. Well, g, all right. G is length over time squared. So we need to add one more length to that. And how can we add one more length to that? ET, if I'm not, work is what, length time? So energy equal to length time. So this is equal to length time squared. Because work, joules, for instance, is equal to meters seconds, right? So if we have joules seconds, then this should be meter squared second. So if we have a length time squared, so we just have to get this, we have to get this out of L squared and the length time squared. So the m we know is going to be 1. And then this is, we need 2 on the top. So we have, let's say we have h bar squared. So that gives us length squared t to the 4th. How do we get length squared without getting rid of the... How do we get the right dimensions with these without giving up our... of these 3 constants, without giving up... Can we divide? So h bar over g gives us h bar g, hold on a second. H bar g gives us L squared. And then we need to divide it by time squared, which is going to be what? H bar divided by g, right? Is that h bar divided by g is equal to L t squared times t squared over L. You get t to the 4th, h bar over g. So if we get this, is going to be on the order of time squared. So if we get m hg over root hg, is this the right dimensions? Because we need it to be m L squared over t squared. So this is now hg has units of L squared. G has, m has, this has units length squared, this is units length squared. This has units t squared. So if we have this times this times this. So now we just need to simplify it. So let's just go m h g times h to the -1/2. And then this is g to the -1/2, I believe, because we've got a negative twice now. So are we not m square root h bar g to the 3/2? So is it not alpha equals 1? Beta is equal to 3/2. H bar is equal to 1/2. This doesn't feel right. I don't feel right about that. But I don't know another way around it. Let me just make sure I didn't do something stupid with my math here. So if we have m h bar g times 1/root h bar times 1/1 over this should be equal to root g, and then this just knocks this back to root g, and we cancel, and then g plus g is this, just 3/2. Ooh, all right, I'm tentatively saying this is the right answer, but I've been getting a lot of the dimensional analysis questions wrong, so this will be something good to get some feedback on soon. All right, repeat to find the characteristic length, time, and velocity for this system. So let's try, okay, let's try characteristic length now. So this is going to be our characteristic what? Characteristic energy. All right, now let's try B. Oh, no, this is B. No, this is 2. Repeat to find the characteristic length, time, and speeds for this system. So characteristic length, I mean, we're not going to use the mass. We've got these two up here. I would say that if it's LT over, it's going to be what? Square root of h bar g. So we've got alpha equals 0, beta equals 1/2. No, this is not h bar. What was the, I don't know, whatever Greek letter this is. So this is for length. And then for time. So, I mean, time, it's this to the power of -4, right? So it would be alpha equals, so for time, just go for length. Again, 0 is equal to, where are we? Is it 1/4? And where are we for velocity? So velocity, we want length over time, and we have length over time squared. So can we put something for length over time? length over time. How do we get length out of time out of these constants? We multiply by time. So our length is this, our time is this. So we could just do these things. So it's just going to be, let's do it up here. Hg divided by but this is so this is 1/2 minus this is h minus 1/4. So this is going to be h to the 1/4. And then this is going to be g, but it's plus 1/4. So this is 3/4. Which one was it? B. B was this one. So 3/4. And this is equal to 1/4. I believe so. All right, so did we get those right? I think given that this is a multi-part question, it'd probably be good to check the answer on this before we go forward, just to see whether we got the right idea here. Again, dimensional analysis was something that I struggle with a little bit. I'm going to just put down the blinds a little bit, get a little bit of glare here. I mean, there's nothing too new about the dimensional analysis, but it's just, again, haven't done it for a long time. So let's go through, and I'm going to open up the solution, and I will just flip it on here just temporarily, and then we can try to open it up, and I'll try to not look at all at question 1 or the other parts of question 2. This is a little hard sometimes, but I'm going to do my very best to just have the ones we're doing. So let's open the solutions. Okay. Where are we here? Gravitational balancing. So, okay. So I was off on this first one here. So I'm going to, oh, sorry, let me just get the, let me get the window so that you guys can see this too. So let me just, how do I want to do this? You know what, I'm going to jump over to this, and then I will just select. All right. I think I should be here. So now we're looking at the solution. Now it's clear that I got something wrong here. So let's figure out how I got it wrong. So in SI units, mass is measured in kilograms, gravitational acceleration in meters per second squared, and Planck's constant in joules seconds, which is equivalent to kilograms meters squared per second. Kilogram meters squared. So I think this was meters per second. So I think this was my mistake, because I think that I got the formula for joules wrong here, because I put it as meters second, and instead it is kilogram meters squared per second. So we wish to find the combination of mass, gravitational acceleration, and Planck's constant that has units of energy. Writing E to this, we have the following units. So let's just look at the solution. I'm going to write the solution in pen so that I can distinguish it from my own work but let's go here. So we have, let me get this over here, kilograms. So we have E is equal to 1/2 mv squared plus mgx. And then the energy we're writing as kilograms meters squared seconds squared equals kilograms alpha meters second squared beta kilograms meters squared second minus 1 theta. So a few things to note about how this solution procedure went. So first of all, what I did is I was trying to find substitutes for the components here, whereas in the solution, they just started with these kind of these coefficients and started with this energy is equal to kilograms meters squared over seconds squared. So this was equal to joules. Now, so this is a mistake of recall for me because I got joules as I was thinking work done over time, but I think it's force done over time, and force is F equals ma, which is equal to kilograms. Right, okay. I was thinking length times time, but it's not. It's force times time, which would be kilograms. Kilograms over meters per second squared times meters per second squared, and then again times another length term. So this is how we're getting it. Okay, so a little bit bad on my part for getting that wrong, but interestingly enough, they have a different solution procedure here for getting at these equations than I was going through. I was trying to solve these equations. They just took it right here. And you know what? I'm going to just look down at this and see if I can just solve this just from the way that it's phrased right now. So we have kilograms alpha plus 1 meters beta plus 2, no, plus 2 this, and then the seconds is minus 2 beta. And then they just have this is equal to 1, so we have beta is equal to 2 and minus 2 beta minus theta 2. I should switch to pencil because I'm doing these on my own, given this hint now. Is equal to 2. So let me just put this right here. Okay. Am I right for this? This one. So alpha is equal to 0. No, that doesn't make sense. It can't be 0. Got a kilogram in the term. got to be 1. Why am I getting 1 here somewhere? Oh, I've written it twice, that's why. No, I didn't. What did I do here? Oh, no, oh, okay. Alpha plus theta is equal to 1. Okay, all right. So let's just solve for theta is equal to 1 minus alpha. We've got beta is equal to, beta plus 2, 1 minus alpha equal to 2, and minus 2 beta minus alpha equal to 2. So we have beta plus 2 minus 2 alpha is equal to 2. Then we have 2 beta plus alpha minus 1 is equal to 2. And then we have minus 2 beta plus alpha is equal to 3. So we have alpha is equal to 3 plus 2 beta. So we have beta minus 2 times 3 plus beta is equal to 0. Beta minus 6 plus 4 beta equal to 0. So we have, is this 5? No, I screwed something up here. I'm going through a little too fast. Did I get this right here? Okay, I did this. So let's just go through it again here. Alpha is equal to 1 minus this. Or sorry, we want to substitute the other way. Equal to 1 minus alpha. So beta plus 2 minus 2 alpha is equal to 2. Minus 2 beta minus 1 plus alpha equal to 2. And then we can take beta equal to 2 alpha. And then we can take minus 2 beta minus 1 plus 1/2 beta is equal to, which formula am I doing here? 2 plus 1. So we get this, we get 3. We get minus 1.5 beta is equal to 3. So divide by this, beta equal to, I'm screwing something up here, 1/3. I got these equations. Solve for each exponent. 1/3, 1/3, 1/3, 1/3, 2/3, 2/3. Did I write this down wrong? Oh, yeah. I forgot a negative sign here. Where are we getting the negative sign from? -2. Oh, yeah, because, of course. No, second squared. Oh, negative. Yeah, there we go. Copying errors. My bane right now. And this is why we're trying to do the dimensional analysis in the first place, is to avoid making these kinds of mistakes. So there's a little bit of irony here, because putting things like the wrong units in the exponents or something like that will lead to incorrect answers, and they're relatively trivial kind of mistakes. So let's try it again. All right. +2 minus 2 alpha equal 2. And let's solve this one here. Beta is equal to 2 alpha. So yeah, we did get that right. And then we have -2 alpha minus, and then y is equal to, so it's going to be -1 plus alpha -2. We add 1, this becomes 1 minus 1. We have -4 alpha plus -1. So we have alpha is equal to 1/3. Plug in alpha to 1/3. Have 1/3 plus 2/3 is equal to 1. So this is equal to 2/3. And beta is equal to 2/3, which are the answers. So in this case, alpha is equal to 1/3. Beta is equal to 2/3. And this is equal to 2/3. All right, without going further, what I'm going to do is now switch over back to the problem set again and see if I can go forward with part 2, given the fact that now we're working with the right equation for energy. All right, so let's try. I'm going to use, again, pencil. I'm going to try to stick to the convention of using pencil when it's my work and pen when I'm copying something, but I don't promise to be consistent with that perfectly. So let's go back to 2 here. Let's just erase our response. And let's try again. So let's use the same strategy that they talked about here. So we've got, we want to have a characteristic length. So let's just use the notations here. I'm just going to put 2 here. Meters is going to be equal to kilogram alpha meters second minus, what am I looking at here? Oh, right, second minus 2. This is the gravitational constant, beta, and then kilogram meters squared second second. Oh, right. Second. That's why, because this is the Planck constant, not joules. And second minus 1. This. Okay. So how much do we want of each of these to get the correct derivative? M. So let's again just add these out here. So we have kilograms. Hold on a second. We want alpha plus psi, or whatever this is, to be equal to 0. We want meters. What do we want here? Here, you know, I'm going to put this down here. What do we want? We want, do I have a sharper pencil here? I'm just going to substitute this. Is a little dumb. All right, so we have kilograms A plus this of meters is meters times beta. Oh, this is the same thing. I'm going to just copy this. Minus 2 beta minus this. So we have this plus this 0. Yeah, plus 2 of this is equal to 1. And minus 2 beta minus this is equal to 0. So A equals this. So we can substitute in beta equal to, no, not this one. So we can just ignore alpha here. I think we know alpha is going to be 0, but maybe not. Okay. We know that that's going to be that. So beta is equal to 1 minus 2 alpha. And then we got minus 2, 1 minus 2 alpha, minus alpha 0. I'm going to have to probably copy this over. Let me see if I can just squeeze it in. So this, we're just going to put minus 2 plus 4 minus alpha. So we're going to have this is going to be 2. And then this is going to be equal to 3 alpha. So alpha is equal to 2/3. We're going to have this equal to 2/3. And beta is going to be equal to 4/3. Beta plus 4/3 is equal to 1. So it's going to be minus 1/3. So we should have for this question, so let's go alpha, beta. This should be 2/3, negative 1/3, 2/3. All right, let's try it again for, sorry, I filled that in over there. Let's see. So let's try doing time now. So So again, we have time, which is in unit seconds. It's going to be equal to, again, we've got kg to the power alpha. And then our gravitational constant is meters second squared beta. And then we have kg meters squared second minus 1. This, okay. I mean, you get seconds from this. So this time we're going to have alpha, again, same equations. We're going to have alpha, what's this, equal to 0. We're going to have, just copy them over, but I don't really want to look back at it. So let's go. Beta plus 2 equal to 0 and minus 2 beta. Did I get those things right there? Yeah. Once again, we can just substitute in. So beta is equal to minus 2 alpha minus 2 alpha minus alpha is equal to 1. We have plus 4. So alpha is equal to 1/3. This is equal to 1/3 minus 2/3 beta is equal to minus 2/3. We have 1/3, 1, 2, 1, 2/3 minus 2/3. So I think this should be, if we go back, alpha is equal to 1/3, beta is equal to 2/3 minus 2/3, and this is equal to 1/3. No? All right, yeah, okay. And then let's do the last one, velocity. So we want meters second minus 1 kg. I'm not going to just keep rewriting this each time. Let's just go through it with these linear equations here. This one's kg, we want 0. This one is meters, we want 1. And this is minus 2b minus -1. Again, beta plus, so beta is equal to beta plus 2 alpha is equal to 1. Is equal to 1 minus 2 alpha. Oh, oops, I'm rewriting the same equation. Let's pay attention here. Minus 2, 1 minus 2 alpha minus alpha is equal to -1. So we have -2 plus 4 alpha minus alpha plus 2 on each side. And we have 3, 1/3, and our equal to 1/3, and our this one here, 2/3. Beta is equal to, no, that can't be right. It can't be -2/3. 2 1/3, 1/3. Oh no, 1/3, 2/3, minus 2/3 is also 1/3. So this is all right. Now let's see if I got any better at this dimensional analysis in the time of practice here. So let's go back over to the solution. And characteristic length of time, follow the same procedure. All right, this yields, let's see if we got this right. In A, we have length is, this should be negative 1/3. This is right, but there should be a negative here. So let me just put the mark here. Should be a negative here. So I got that wrong. 1/3 and then 2/3. So that's right. Time, we've got should be negative 1/3. No, yeah, negative 1/3. I must have screwed something up because I've got the signs wrong on all of these. Negative 2/3, 1/3. Did I get this right? This is 1. So how did I get the plus this? Oh, you know what? This is again, I'm doing my algebra wrong. I'm substituting this out here. This is, in these, I'm doing this, so I'm saying A equals this, but it's actually A equals minus this. Yes. All right. So this is why I do these problems, is because often you haven't done it for a while, you've got some errors, you've got some rustiness in there. So there's definitely work you can do. These problems is what I need to do right now to get better at this. And these are kind of silly mistakes in the sense that, I'm got these answers off because I'm doing the algebra too fast or I'm not seeing my mistakes. But on the other hand, this is also how you have to get the answers right. So let me get back here. Question. So we're going to leave it there and we're going to go on to part 3 here. And you know what? I'm going to look for just a second. I'll keep using this for right now, but I might have to take a little break to go find a pencil sharpener because this is getting a little dull. So 3, classically, putting the system in its lowest energy configuration, E equals 0, would require the particle to sit perfectly still, V equals 0, precisely on the surface, X equals 0. Using the uncertainty relation, to argue briefly that the particle cannot have E equals 0 while respecting the uncertainty principle. How do they want me to show this? That's the question I have, because I think that's obviously the case that if we have delta X, delta P greater than or equal to H bar over 2, well then X can't be definitely 0, right? So what do we want to do? Are we supposed to be using dimensional analysis to show this? Yeah, I don't really know what would count as showing this to argue. But it means either that the MV or X has to be well, basically this just I don't really know how to show this. I'm just gonna leave this one here as like X is positive, and this is positive, ergo yeah. I'm not sure what a solution of this looks like. I'm going to just leave this 3 for right now. Let's move on to question 4. Use your dimensional analysis results to give a simple estimate for the ground state energy of the system. How does your estimate behave as h goes to 0? How does this make sense? Explain why or why not. Well, I'm assuming we're thinking the ground state is on order of the dimensional analysis, and if the dimensional analysis gave us the energy, which were the coefficients of that. Coefficients of that were, I didn't write down the actual answer. Right here. The coefficients of that were 1/3, 2/3, 2/3. So we have mass 1/3 g 2/3 2/3. So we're assuming this is E0 is on this order. How does your estimate behave as h goes to 0? Well, as h goes to 0, E0 goes to 0. And does this make sense? I mean, it makes sense in the sense that if there's the uncertain relation is defined in terms of this Planck's constant, so I would imagine that makes sense. Okay, I'm not going to be able to explain this, but I think that's what we're trying to say here. And then V, estimate E, L, T, and V numerically for a neutron. This mass, how high above the surface will the particle typically be found? Okay, so I'm going to do this, and then I'm going to check all the answers to this question. So we know that Mn is equal to, so M is equal to 1.7 times 10 to the negative 27. So we have 1.7 times 10 to the negative 27, power of 1/3, times 9.8 meters per second squared, 2/3, and then we have what do we have? What is Planck's constant? What is Planck's constant? Let me find it again here. Planck constant 17. So Planck's constant in joules second is, I'm just going to slide this guy over here. So we can see, I'm just copying it down. This is 6.6262 times 10 to the negative 34, the 2/3. So this seems like a problem best handled by a calculator, so I'm going to just do this on my phone. Let's see if I can do, although perhaps I will get a calculator if I have to do this a lot more. So we have 1.7 times 10 to the negative 27. Oh. Oh, oops. No, my phone calculator is not the best tool for this. I'm just going to enter on the computer because I'm tapping buttons by mistake here. Mm-hmm. Actually, let's just do the square roots of these things here. So 1.7 to the power of 1/3 is equal to, so let's go 2.02892 times 10 to the negative 27 divided by 3. And then 9.8. So I can just figure out this one. 9.8 to the power of 3 to 4.57949. And then this last one is going to be 6.6262 raised to the power of 2/3. And then this is times 10 to the negative 68 divided by 3. And so 27 divided by 3 is 9. And 68 divided by 3, I'm not going to do that one. It's like 20, 22 point. 22 in the third. So 22 and a third. Hold on a sec. I will just reformulate this question so that I don't have a weird answer here. Like 5, 2, 7, 8, 4 times 10 to the power of negative 68 divided by 3. Oh, what did I do wrong here? 3.5, 2, 7, 8 times 10 raised to the power. It's not working for me. I don't know why. I must be typing something wrong. So we have 10 times the negative 22 times 10 to the 2/3. So I'll just multiply that one out. What's going on here? Okay. 4.6. So, oh, sorry, 2/3. Is it negative 2/3? Yeah. What am I doing here? 10 raised to the power of. See, we have this. Why is this not working? 10. I don't know why I am struggling with this calculation here. I've got to get a better calculator. All right. This is our rough estimate here. I'm going to leave this calculation untouched for right now. Let me just change this back to what I had before, as it should be something numerical, and I will look at it after. So let's just move on to B. I think I want to just go on to B, and then I'll check these problems after. All right. So the scale at which gravity, characterized by Newton's constant Gn, quantum mechanics, and relativity are all important is called the Planck Scale. Using dimensional analysis, find the combination of powers of Gn, h, and c, which make a length. We'll call this the Planck length. Okay. So we can do the same formula we had before. Length is going to be in meters. Newton's constant Gn is, what are the units of Gn? Let's not make the mistake of last time and just guessing and then getting it wrong. Newton's constant. Oh, it's not saved here. I'm just going to have to find it in gravitation. Let's just go back to the beginning of this chapter. Find Newton's constants. Okay. Gravitational constant uses is force. Now, force is equal to kilograms squared. No, hold on a second. force is equal to mass times acceleration. Force is equal to mass times acceleration. So therefore, we have meters divided by second squared times kg, and then this is times meters squared divided by kg squared. So this is our gn. So let me just, I'm going to put this first. Gn is this. So we can cancel one of these, cancel this, and we get meters to the third, second to the minus 2, kg to the minus 1. It's for gn. Then we have h bar, which we already know was, let's see if I can recall it from memory. H bar is kilograms. It's again a force times a distance. So we have kilograms meters squared. And then there's an additional second, so we lose one of these. And then what was the last one? C. Okay. C is the, I think this is meters per second. I'm going to feel stupid if I didn't get it right, but let's check. I think C is just speed of light in a vacuum, so it should be meters per second. Let's confirm that I'm not crazy here. Speed of light. Speed of light. 8. Hold on a sec. 8 here. $860. Yeah, see, this is just meters per second. I'm not going to worry about this one. Okay. So let's go through here and do this one like we did the other ones. So we want to get meters, and we need to have some amount of Newton's constant. So we're going to have Newton's constant, which is this thing here. Some amount of this, which I'm going to put them in the same order. Mu squared minus 1 kg. And then C is going to be meters minus 1. This, okay. So our formulas are going to be three. So this is for, I'm just going to put it as this is for meters. 3 alpha. Three alpha plus 2 beta plus this is equal to 1. And then we have for our second scale, minus 2 alpha minus 1 beta minus this. I'm just going to put this one here. This is equal to 0. And then we have kg. We're going to have minus alpha plus beta equal to 0. All right, so beta is equal to alpha. We can say that right now. So we can rewrite these top two equations too. So let's turn them all into alpha. 3 alpha plus 2 beta. No, what am I doing? Plus 2 alpha plus this equal to 1. So we have 5 alpha equal to 1 minus this equal to minus. All right. We can probably do it the other way. That makes more sense. Let's solve for the other way around. One minus 5 alpha. And then we have minus 2 alpha minus alpha minus 1 minus 5 alpha 0. Minus 3 alpha 5 alpha equals 1 over 1/2. All right. Beta is equal to, if alpha is 1/2, beta is also 1/2. And this is equal to 3/2 plus 1 is equal to 5/2 minus 1/2. Let's just check that. This is -1 minus 1/2, -1/2 is equal to alpha. Okay, so this should be okay. And then, so to go for this question, I'm just going to put the first question here. So for the characteristic Planck length, we've got, what do we have? Well, we have it's equal to all over the square root of, which ones were which now? It was Gn over C. This is the characteristic analysis. All right. Now 2. Evaluate LP numerically and compare it to a typical scalar for nuclear particle physics, namely 10 to the -15 meters. So I should really get a list of all these. So Gn is equal to what numerically? So this is equal to 6.67 10 to the -11. And then our H bar, I wrote that down before, it's equal to 6.6262. 6262 times 10 to the -34. And then c is equal to, I think it's 3 times 10 to the 8th meters per second, more or less. So if we evaluate this numerically, what do we have here? The Planck scale is roughly square root of, so I'm just gonna ditch these constants so I can just get this a little bit easier. So it's essentially 10 to the minus 43 divided by 10 to the 10 to the 8th. So this is approximately the root of 10 to the root negative 51, either 51 or 52 is equal to 10 to the negative 25. I think that's about right, 10 to the negative 25. This is my estimate, approximately. So this is roughly 10 orders of magnitude smaller than nuclear scale. Okay, so this is an estimate. I didn't do this exact calculation. 6 times 6 is 36 divided by 3. Probably one more digit on the top there. So this is probably 42. It's probably 50s. It's about this, I think. It's going to be off by a bit of a factor, but I think it should be roughly right. Let's go 3. Repeat to find the Planck mass. All right. So MP, let's just copy our approach from before. So this time we're doing kg is equal to, I'm going to try to recall the formula. So I could go back and check those equations again, but I think it's useful because I need to drill into my head the dimensions of these common constants, because otherwise it's just going to be a pain. I'm not going to be able to see it when I need to do it. So this is an example of something I do actually need to memorize in physics. So the first one was Gn, and now Gn, I'm just going to close this book. Gn was what? Gn was force times Gn was newtons times kilos All right, let's see what it was. It was, oh, okay, so it was meters cubed, seconds to the negative 2 kg to the minus 1. Was that right? Okay. All right, let's do h bar again. H bar I should be able to remember now. It was joules seconds. Joules is 4 seconds, so that's kilograms meters divided by seconds squared times another meter. Let's subtract another, so it should be kilograms meters force is meters per second squared. Meters times joules is going to be times meters again. So this should be meters squared. I want to say that's right. Yeah. And then the last one was meters seconds. Okay, there we go. So let's try this out again. So we have, let's see if I can double check my last formula, so I should be able to get it right. So we have 3. So let's first start with meters. 3 alpha. 3 alpha plus 2 beta and we don't want mass, so this is 0. We don't want meters, so this is 0, and then this is seconds. We have minus 2 alpha minus beta minus this equals 0. And then we have kg is going to be minus alpha plus 2 beta. No. Plus beta. Got to be very careful. Plus beta is equal to 0. So again, alpha equals beta. So I'm going to double check that that's what I got the last time. Okay. So alpha equals beta. We go 3 alpha plus 2 alpha plus this is equal to 0. So we have this is equal to minus 5 alpha. And then we have minus 2 alpha minus alpha plus 5 alpha is equal to 0. So we have minus, is that right? I must be missing something. All right, let's try this again. Alpha equals beta. This is 5 alpha. Goes minus 5 alpha. That's a minus 5 alpha. Oh, minus 2 alpha. Minus alpha. Minus. So alpha is equal to 0. Beta is equal to 0. No. So there's a possibility I set up this linear set of equations wrong because I'm only getting degenerate solutions. Did I forget something? So this is what I had last time, is it not? 3 plus 2 plus y equals 1. Minus 3. So this analysis is saying I can't find it from that scale. But that seems to be I must be missing something here. I must have made a mistake. All right, I think, were there any problems that we had skipped over here? Skipped over numerically calculating this one. But yeah, I think I'm going to jump back to the solutions just because we've covered some stuff now. I want to get a little bit of feedback on it, and I've definitely made a mistake here. Now, maybe it was I wrote the, it could have been that I wrote down this wrong. Because I seem to be getting some kind of degenerate solutions here. So let's go to the solutions and let's see what they say. And then we can jump back and get back to work. Okay. So let's go through the, let's go back to where we were before. P2. So I got these, but I had an error in that. So let's go to 3 now. 3. Having the particle sit completely still would mean that there would be no uncertainty in its momentum, equals 0, and having it be precisely on the surface. Okay, well, right, that's basically what I said. So that was a kind of qualitative question, but I think I got the good answer. V, the energy of a system given by this, plugging the nearest length. Oh, okay, hold on a second. One half. Okay, but that's what we did calculate, right? This is math. Okay. All right, so I did get this right. I didn't include this little digression into, did it ask for that? Yeah, okay. All right, so I feel pretty good about how the question was asked, although there's some more information here. Plugging into the neutron. Length is this, this is this, this is that. Okay, so this, I'm going to actually have to mass of a neutron, 27 kilograms, gives E equals approximately this many joules. Length, oh, okay. So, all right, this one here, I'm going to just omit that from my discussion right here because it's just a numerical calculation. But all right, BI. The SI units for GN are kilogram to -1 mass. So is that what I got? Yes. Kilogram mass squared. Yes. And C are yes. Okay, so I did get that correct. Let's see if I got the actual answer right, which I should have been. So where did I get here? I have, so we have, what do we have? I've got this. 3A. This is right. And what's the other one? This is also right, but I did the calculation wrong, it appears. Got 1/2 and 3/2. So this, they've switched theirs around, but this is 3/2, which I must have done. 1/2. 1/2. Yeah, okay, so this is wrong. I'm going to change this here. All right. Okay. Not too bad, but okay, now that this is 3/2, this is actually to the cubed. And because this is to the cubed, and I did not get that correct. So I need to be better about checking my work. So this to the third means that this is going to be 24, which is going to be, instead of 43, this is going to mean this is, or 42. Let's change this to 42. This is going to be 64. So probably 32. And because it's 32, I think it was 15. It's another 10 orders of magnitude. There's 22 orders of magnitude. Gives this times this. Wait. I have here 6.62. Oh, because this is h. And I've got h bar, which is divided by 2 pi. Root 2 pi, 2 pi. So it's not this. Okay, good to note. All right. All right. 20 orders of magnitude, yeah. Okay, now 3. Why am I screwing this one up? Following the same procedure gives this. So let me just try it again, because maybe I'm missing something obvious here. This is right. I mean, I switched around the beta and the y, but that's right. And this is right. But we want... I set it up and I put zeros for everything. That's why I got that wrong. Wow, okay. These are normal, so I'll just say this right now because I'm going to just switch over and calculate it again. Hold on a sec. Which scene do I want here? So if you are happening to watch me right now, I'm making a lot of mistakes going through this problem set. Now, a lot of my mistakes, some of my mistakes are concept problems, so I'm making mistakes. A lot of my mistakes are just, I'm setting up the equations wrong. I'm doing simple arithmetic errors, simple algebra errors. These are all coming from not having done this for a while, not being as practiced, not catching my mistakes. Now we'll see. I'm not necessarily going to be able to get world class at this in a month's time, given that I've got a lot of years of rustiness that's coming here, and I think that a lot of these problems are just going to get resolved from just working on them. But at the same time, I actually find that having these algebra problems is actually a good sign, because it's worse to just not understand what's going on with the problem. So here, I mean, making some simple mistakes, I've got to get a bit better at that, but that's what doing the problem sets are for. That's what it's good to practice for. So let's try it again and see if I can get the right answer this time. So again, we're looking at this question here, number 3, trying to find the Planck mass, or the Planck mass. So once again, going slowly, beta is equal to 1 plus alpha. So then we just do 3 alpha plus 2, 1 plus alpha plus this equals 0. We have 3 alpha plus 2 alpha plus this equals 0. 5 alpha this to minus 2. Minus 2 minus alpha. And then we want to substitute that in here. So minus 2 alpha minus minus 1 plus alpha plus 2 plus 5 alpha is equal to 0. So we have minus 3 alpha minus 1 plus 1 5 alpha 0. So we have 2 alpha 1 equal to negative 1/2. So we have 1/2 plus beta is equal to 1. Beta is equal to 1/2. And this is equal to, what can we do here? Negative 3/2 plus 1 plus this is equal to 0. So this is negative 1/4. That's equal to 1/2 as well. So let's calculate this out numerically. I'm just going to leave this open on that side. So what do we have? We have, it is, alpha is negative 1/2. GN's below. And we have beta, which is 1/2. Above, which is this, which is this. Okay, let me just double check because I've been making a lot of mistakes. Am I at all close here? What do we have? Yes, okay, we get this question. This is correct. And now let's, if we calculated this h bar, which I had the wrong constant for. So h bar is 1.05 times 10 to the negative 34. And g is equal to 6.67. Okay, so I did have the right one for that. And times 10 to the 8th. And so let's work on this here. Planck mass is going to be square root of 4 times 10 to the 8th divided by 10 to the negative 11th. So we can just take these. So 34 minus 8 is 26 minus 11. I guess I can just do this. Is equal to 10 to the negative 15. No, this seems too big. What am I doing wrong here? This seems like ten to the negative, I don't know, 10 to the negative 8-ish. Oh, it is. Okay, it is 10 to the negative 8, so that is kind of right. But so I guess what we're saying is the Planck mass is much greater than proton mass. So what is the proton mass? Proton mass is to negative 27th. Okay, yeah. All right, so that is the end of question 2. I'm just going to take a 2-second little breather here and focus on what we've been doing. So I have been going back and forth between the problem set and the solution. So from an evaluation standpoint, this problem set's not going to be very useful because I'm jumping back and forth so much. It doesn't work as a test, so to speak, of like how well do I know this information, because I'm making mistakes. I'm going back and checking, fixing from that feed, getting better answers going forward. But at the same time, I try to treat most of this as a learning opportunity. So when I'm looking at the mistakes I'm making, I mean, the dimensional analysis, I was not doing that right in the beginning from a conceptual issue. I was getting kind of stuck on it here for kind of conceptual reasons. Once I got this kind of, okay, solve the linear equations, which I mean, in retrospect, I should have figured out, but I haven't done this kind of equation before, or I haven't done it recently, so it didn't occur to me. And then I have made other mistakes since. And some of these mistakes are having the wrong constants, having the wrong formula for for work is one of them. But in other cases, it's me making stupid mistakes like setting up the linear equations, having them all equal to 0. I mean, again, this is a silly mistake. This is something that I shouldn't have to think about if I have mastered the previous classes. But one of the things I'm going through this class with is that I'm rusty with a lot of this stuff. I kind of remember, I forget a lot of details. So part of this is just also kind of get me back into doing these kinds of equations, these kind of problem solvings, which I haven't done for 8 years. So I think also we're dealing with like some of these numerical questions I was doing with the calculator, but honestly, I don't think that they're going to show up much on the actual MIT tests. I've very rarely been asked to actually use a calculator for something, but if they're coming up more and more, I'll make sure I get a calculator so I can calculate these things and not have to just guess on it. All right, so let's move on to question 3. De Broglie relations and the scale of quantum effects. All right. 3A, light waves as particles. The photoelectric effect suggests that light of frequency nu, I guess, I think that's nu. I also have to learn how to pronounce my Greek letters. Nu can be regarded as consisting of photons of energy E equals h nu, or H equals this Planck constant that's not modified by a scale factor of 2 phi. Visible length has a wavelength in the range of 400 to 700 nanometers, with the energy and frequency of a photon in visible light. So let's say visible light is 400 to 700 nanometers. We know that speed of light is equal to 3 times 10 to the 8th. So if we have 3 times 10 to the 8th, and this is the wavelength, the frequency is going to be so 400 times 10 to the negative 6 meters divided by times 10 to the 8th squared. Hold on a sec. Frequency, I want 1 over the time. What is the frequency? Let me just get my bearing straight, right? This is the wavelength. Oh, probably should do a full sine wave here. Wavelength, and we want it goes this far in 1 second. If it goes this far in 1 second, then how many times did it go up and down in 1 second? So that's 3 times 10 to the 8th divided by 4 times 10 to the negative 6 is equal to 0.75 times 10 to the 14, or 7.5 times 10 to the 13 to 700, which is going to be 3/7. 3/7 is, let's get a rough number here. .42. All right. So that calculation should be correct. I've been making mistakes before, so I want to just go through one at a time at this stage. So I'm not going to switch it just because I'm just checking this one formula here. 4.28 times 10 to the 14 hertz. Did I do a miscalculation somewhere? Ten to the 14 hertz. Why do I have 13 written here? Oh, 400 nanometers. So it's 10 to the nanometer is right. So this is 400 times, right. Okay. So this is 14 because a nanometer is meter times 10 to the negative 9, but we've got 2 digits there, so we got 7. So, okay. All right, and then what do we have here? We have energy of light. So we need E is equal to 6.63 10 to the negative 27 erg-second times frequency, which is a, so let's do times, let's do this one here, 7.5 10 to the 14. So this is going to be like, I don't know, 44.5, add an extra 1.5 times 10 to the negative. This is 6. Then we have 6 minus 1, 4. And minus 12. And if it's 4.2, then we're looking at maybe 2.4 to 4.5. All right, let's check if that's right. 2.84 to 4.97 joules equals 1.77 2.10 electron volts. Okay. I think, this is in ergs. What is ergs to joules? don't feel as great about that. What is an erg? Let me just get the definition of erg up here. Centimeter, gram, second unit of work. 10 to the negative 7 joules. Okay. So what? Erg is 10 to the negative 7 joules. So if I have this, then this is erg, then 4.5 times 10 to the negative 19. So yeah, I didn't do the math with the calculator, but I think it's pretty close. All right. This is 1, 2. The microwave in my kitchen operates at roughly 2.5 gigahertz at a max power of 7.5 times 10 to the 9 erg per second. How many photons per second can it emit? So 2.5 gigahertz, 2.5 times 10 to the 9th is the frequency. If I'm not mistaken, gigahertz should be 2.5 times 10 to the 9th equals 2.5 gigahertz. And a max power of that. So what is the energy of this? Well, we have E is equal to 2.5 times 10 to the 9th times, what do I have here? 6.63 times 10 to the minus 35 here. 35, 34. Seven more than this, 27. All right, joules. I can do it in joules. Oh, this is in ergs, so I got to keep it in ergs. 27. So this is, we'll just get rid of this, lose 9 here. 10 to the negative 18. And this is, it has 7.5 times 10 to the 9 erg. So we need 7.5 times 10 to the 9 erg divided by 6.63 times 10 to the negative 18 erg. So the amount of photons is going to be on the order of 10 to the 27 photons per second. That's a lot of photons. What about a low power laser? So this is the microwave. Laser is going to be 633 nanometers is, where are we? I'll just use this example. So I'm going to say 10 to the 14 because 633 is in this visible light radius range. So I'm going to recalculate 10 to the 14. Sorry, not 10 to the 14. 10 to the negative 12. So it's going to be 10 to the 4th divided by 10 to the negative 12. So it's going to be on the order of 10 to the 16 photons. And cell phone, 4 times 10 to the 6. $850 megahertz. So megahertz is times 10 to the 6. So 8.5 times 10 to the 8th is the frequency times 6.63 times 10 to the negative 27. So we are going to multiply these two. Again, order of magnitude here, we're going to have 6 times 8, you know, let's bump it up by 1. So if we have 9 minus 27, again, 18. If it's 18, then we're looking at, so this is on the same order of magnitude as the microwave for the energy per photon. And then where are we here? What's the amount it's suggesting? 4 times 10 to the 6. So let's say it's 10 to the 6 divided by 10 to the negative 18. Is equal to 10 to the 24. So let's just look at these. I'm not going to be exactly right. I didn't want to get out the calculator and do all these calculations, but I wanted to have a good approximation of it. 2.5 gigahertz, each photon carries 10 to the negative 17 ergs. That's, yeah, I said 10 to the negative 18. 2 to the 20, yeah, I had 10 to the 27 on the order. Okay. Laser, 10 to the 15, I said 10 to the 16. And 10 to the 23rd, 10 to the 24th. So I'm like, yeah, I'm on the right order of magnitude for these, roughly. Okay. Next, let me make sure you guys can see this. Next, let's do where are we? How many such microwave photons does it take to warm a 200 milliliter glass of water by 10 degrees Celsius? So we have 0.2 liters. Heat capacity of water is well, that's per gram. This is 200 grams. So we have 4.18 times 10 to the 7. So we need for each degree, so we're going to add this because we want 10 degrees, we're going to have to add it up by 10. And there's 200. So we're going to multiply this by 200. So we're going to have, again, 8.2 or 8.36 times 10 to the 11th. So we need this many ergs to raise it up to the temperature. And the microwave photons are we need microwave photons were, how much were they? 10 to the 10 to the negative 18. What did I figure out? What was the frequency there? 10 to the negative 17, right? So we have 8. So we have 10 to the 11th, 10 to the negative 17. So we've got on the order of magnitude of 10 to the 28 photons required. And at a given power of an electromagnetic wave, do you expect a classical wave description to work better for radio frequencies or for X-rays? I'm going to say radio because more photons. All right, so let's check those answers. Oh, I got one too high there. So 27. All right, yeah, close enough. X-rays are much higher frequency, many more photons. The radio waves in statistical description, classical description. That's why radio astronomers almost never have to use quantum mechanics, whereas X-ray astronomers use a photon description of light in their work. Very interesting. All right. B, matter particle as waves. If the wavelength can be associated with every moving particle, then why are we not forcibly made aware of this property in our everyday experience? In answering, calculate the de Broglie wavelength lambda equals h over p of each of the following particles. An automobile of mass 2 metric tons traveling at the speed of 15 miles per hour, 22 meters per second. So, so this is equal to h over p. So for the truck example, the p is equal to momentum is equal to mass velocity. So this is 44,000. And this is 6.26. What was it? 6.26. What was it? 6.2, 6.63. 6.63 times 10 to the, do I want it in ergs? Broglie wavelength. It's going to make a difference. Is it going to make a problem that I'm doing this in ergs and not? I think so, because it's the wrong units of centimeters. So I think I got to go up to joules. So joules was what, 34? So this is, 6 divided by 4.4. I mean, it's 1.5. 1.5 times 10 to the, and then we've got 10,000 here, 10 to the 4, 10 to the negative 30 meters, roughly. Let's see if I'm right. Oh, 1.538. Now why 38? Oh, I'm silly. I've been so used to doing these things with negative that this is 4.4 times 10 to the 4, so it's 38. All right, yeah. Okay. 2. A marble of mass 10 grams moving with a speed of 10 centimeters per second. All right. So 10 grams is 0.0. So 0.01 kilograms times 0.1 meters per second is equal to 0.001, which is equal to 10 to the negative 3. So we need to subtract 3 from this. So it's going to be 6.63 times 10 to the negative 31. Okay, yeah, that's right. 3. A smoke particle, diameter -5 10 to the negative 5 centimeters, and a density of, say, 0.2 grams per centimeter cubed, being jostled about by air molecules at room temperature, T equals 300. Assume that the particle has the same translational kinetic energy as the thermal average of the air molecules. Ooh, okay, all right. So how much mass does it have? Let's start with that. So 10 to the negative 5 centimeters, 0.2 grams per centimeter cubed. So it's 10 to the negative 15th centimeters cubed times 0.2 grams. So it's going to be mass is equal to what? 2 times 10 to the negative 16th grams. And then the particle is the same translational kinetic energy as the thermal average of the air molecules. KB equals this. Yeah. So we have KE is equal to 3/2 1.38 times 10 to the negative 16th times 300 is going to be equal to 450 times this, or I mean 1.5. I mean, this can be like 600, let's say. So 600 times this, let's just say 6 times 10 to the negative 14 is the kinetic energy. So if this is the kinetic energy, that's 1/2 mv squared. So 6 times 10 to the negative 4 is equal to 2 times 10 to the, we'll just change this to 1. I mean, I'm not really doing the, and then this is v squared. So we'll subtract this, and it's 6 times 10 to the negative 14 plus 16, 6 square root of 600. This seems fast. I think I might be, did I do something wrong? Square root of 600. What times what equals 600? 25 times 25, no. We'll do that on the calculator. Yeah, 25. So V equals about 25 meters per second times this. I mean, we're losing one significance, so the momentum is 10 to the negative negative 15th. 10 to the negative 15th is the momentum. 10 to the negative 34. Looking at what? 10 to the negative 19 meters, roughly. Let's see if that's right. As a sphere. Oh, okay. So I'm off by 5 orders of magnitude, so that's not close enough. Oh, because I have 25 meters a second. This is 0.34 meters per second. So what am I doing here? Negative 16 grams. Did I guess that? Yeah. I mean, 2 to the negative 16 grams. 1/2 mv squared equals 3/2 kBt. I must have just done something here, right? Mv squared and negative 14. $300, 3/2 kBt. Why is that not right? All right, I'm not going to sweat that one. I'm not doing the exact calculation, but I think I must have just done something when I was doing that calculation there. All right, let's do 4. Rubidium atom has been laser cooled to a temperature of 100 microkelvin. How much does a rubidium atom weigh? I don't know, let's just check that real quick. How much does rubidium weigh? Yeah, I'm not going to be looking up this right now. I'm just going to leave this one. All right, let's go on to 4. Electrons of momentum p fall normally on a pair of slits separated by distance d. What is the distance omega between adjacent maxima of the interference fringe pattern formed on the screen at distance d beyond the slits? Note, you may assume the width of the slits is much less than the electron de Broglie wavelength. This, I think, is another 803 question that I potentially did not do. So let's see if I can reason about it, but it may also be something that I want to come back to later rather than just look at the answer right now. So we have these slits. This is D. This is D. What is the distance W between adjacent maxima? So this, I guess it's omega. So we're assuming some kind of wave like this, right? the question is how far across are these, which is basically by saying we've got corresponding to the wave crest here and the wave crest here, then the next maximum is going to be the subsequent wave crest here and the next wave crest there. So we know that this distance is going to be the wavelength of the electron. Is this electron? Yeah, electron. That doesn't necessarily correspond to this. I think this is a trigonometry question that we can just do with trigonometry. So let's try to do it with trigonometry. So basically, let's just go here. We've got, this will be, we'll call this is d divided by 2. And this is where maximum one hits. And then along this axis, we're going to have another, this is going to be units of lambda along this axis. So these are spherical waves, we're assuming. The two crests, this is crests. And then this is along that direction. And so the question is, if this crest hits here, then where along this thing where does this hit? So let me write it out again. I think I can solve this with just trigonometry. Okay. This is d divided by 2. This is, just Pythagoras' theorem. We can figure out this one. Then this is this side minus a lambda. And then we take this distance and figure out, presumably it's smaller than this. I'm drawing my thing too big for it to be physically meaningful. Let's just make this smaller here. And then the question is, when does this second crest hit here? And I think because of symmetry reasons, it's also going to hit on the other side, no? Well, let's just solve this right now, and this might give us an answer. So we take this radius out. We need a point here where this distance, so these two are the same size. And then the question is, how far apart is this? So d squared plus d squared over 4 is equal to this length. But what we want is the length minus lambda. So d squared plus d squared 4 plus this is equal to L minus lambda. we want to know where does this strike here? How do I figure that out? Do we know what that distance is? I mean, it's kind of a circle at that centered here. So we know that the radius of the circle, this is the radius of the circle. And the question is, where does it pierce this? Presumably we know what this is if we can just solve it this way, though. I don't think I need a circle. So we know what this is. It's this minus omega. So this hasn't changed. This distance is still d. And this is, so we have d squared plus d squared over 4 minus 1 wavelength. Is this distance. So if we get this squared, sorry, I need to do this first. Squared plus d raised to minus squared, no, sorry, equals plus d squared. That makes sense, right? So, see if this works. Let's just expand this out, I guess. So we've got minus 2 root d squared plus 4 plus y squared, or plus lambda squared, is equal to d squared over 4 minus 2, which is going to be minus e squared. So we can cancel this, cancel this, cancel this, cancel this. What do we have left? We have we'll just recopy this here. We have minus 2 square root d squared so I'm just going to move this over. Equals negative d plus squared. All right. This looks like an awful quadratic equation. I'd rather not solve right now. D W plus 2 root d squared 4 oh, am I gonna have to do the quadratic formula? Don't really feel like doing the quadratic formula. Let's do it. It's quadratic formula is equal to b squared plus or minus let's do a quick check. All right, so minus b plus or minus of b squared minus 4ac over 2a. And then what are we going to have here? Well, this is going to be d plus or minus square root of d squared minus 4 times 2 root. So equals plus solution equals d plus. See if this simplifies to anything. Otherwise, I'm going to check the answer because this is probably something that there's a formula I'm missing for. E squared minus maybe we can just bring the 2 under the square root here and cancel some things. So we have this. This is equal to it's going to be one of these solutions. So I have a feeling that this is probably not the right answer. Let's see how they solved it. Where's 4? Is there a question here? Oh, yeah. Conditions for constructive. Oh my God. All right. So it was, what was it? It was d sine theta m equals m lambda. All right. This is an example of waves. I just didn't have this formula, so I'm trying to do it with quadratics. I think this was the wrong approach. Let's try to understand this formula, why it works, but otherwise I don't think that there's much to be done here. So we've got the I guess we got, and then there's going to be constructive. Here and here, and then so how do we get this? M is the order of the maximum. Why is this true? Why is this the case? D sine theta. I think we just have to take it. So, all right. Something I'm missing here. D sine theta. We're looking here. Oh, here. There we are. D sine theta. So let me write down what their answer was here for this starting point. Sine theta to y or d. So if we have this, what am I missing here? What do we have to do? E sine m. What is the theta here? I don't know what the theta is. Is it the angle between them? Like, I guess this is theta. Let's just look at what they have here for the answer here. Sine theta. I don't know what the theta is. All right, let's just jot down this answer here. D over D m is equal to lambda Well, that was a lot simpler than what I did. All right, let's try the next question without looking at the answer here. All right. In an experiment performed by Janssen in 1961, electrons were accelerated through 50 kilovolt potentials. Potential towards two slits separated by 2 to the negative 10 centimeters and detected on the screen 35 centimeters beyond the slit. Calculate the electron's Debroglie wavelength and the fringe spacing. All right, well, this is going to be equal to, what did we decided? This was equal to H over, not H bar, H over momentum. And so the momentum of the electrons is going to be equal to H over the electrons mass times their velocity. Mass of electron times velocity of electron. Velocity of electron is equal to, well, from the kinetic energy formula, we know that it went through 50 kilovolt potential. So kinetic energy is going to be equal to 50 kilovolts, right? Wow, 50 kilovolts is the kinetic energy. Actually, this is momentum. It's massive. So, what is our I should really write down a lot of these constants if we're working on this problem set. So basically the apparatus of this experiment. We drop an electron for 50 kilovolts. So it's accelerating in this time frame. That will get us our velocity. This will get us the wavelength. And then the fringe spacing is, if we go back to the solution from the last problem, which we were missing a formula for, we should have lambda dd. So let's get, that's lambda d is what? D is 35 centimeters. So this is 35 centimeters is 0.35 meters. And then these are going to be 2 times 10 to the -6 meters. And so we just need to find lambda. And to find lambda, we just need to find the velocity of the kinetic energy, 50 kilovolts. Is there any way I can go from energy directly into momentum? I don't think so. I have to find all these constants out. You know what? I'm going to pause it right now. Just going to leave this in here of where I left off. It's been a long day. I've been at this now for considerably over 7 hours, so I'm feeling a little bit hazier in the head. I'm just going to shift over now to putting the notes away right now and just talking about what's going on. So where did I end up? Well, one of my goals was to get to the first 10 lectures. Got through those 10 lectures. Clicker questions in the lectures gave me reasonable confidence, my conceptual understandings in terms of the material covered in this particular, these particular 10 lectures. The things that were a little bit tricky for me were how we got to the raising and lowering operators, although I understand how they work, as well as the brute force differential equation. And so there's going to be a question of whether or not we want to go back and deeply understand those things. I think we probably will, but it also depends on what's a bigger priority, because I don't think that those derivations are going to play a large role in working with the equations once we understand them, but it's part of my goal of getting this intuitive understanding of quantum physics. We're working through problem set 1. I anticipated that problem set 1 was going to be difficult because it's all old stuff. So it's not stuff that I just covered in the last couple of days. It's stuff that I covered 8 years ago. So I'm, bringing out, oh, right, how do you do this? How do you do that? And I haven't done a lot of, algebra for these types of problems. So I'm making silly mistakes. So some examples of silly mistakes that I've been making in this one here. Trying to solve a system of linear equations where everything is equal to 0. So this was something I just forgot to put the 1 on the side, and I'm, breaking my head over doing this because this should have been obvious that I shouldn't be able to do that. Now there are silly mistakes. I'm thinking that energy is, or the calculating the wrong units of one of these formulas, picking some of the wrong equations. Again, simple arithmetic errors. A lot of these questions I was getting okay in the middle. The first question, which we were dealing with, which was the classical collapse of the atom, I got kind of stuck because I don't know, I wasn't quite sure how to get the stable orbital velocity for the electron. I mean, I know that it's got the Coulomb force, but I was trying to figure out, okay, how fast is it going around there? Because I need that to figure out, how fast is it going? Therefore, in one revolution of the atom, how much energy should be lost according to this formula? Struggling a bit with that. Now, I have a good feeling that this was covered in waves because they even mention it in that question. So I may be banging my head against the wall for no good reason for this question. Maybe just the kind of question that I want to just look at the answer and move on. It may be the kind of question that if I don't understand the reply I get in the answer, that I want to do a little bit of studying from 803. I don't really feel like taking all of 803. I think that even though it is sort of required for this class or is recommended for this class, I feel like I can probably get away with not knowing it on most of the questions. So this problem set 1 is leaning more heavily on not only 803, but 801 and 802. And so I'm making some mistakes. There's a lot of numerical questions in this one too, and I did not even think to put a calculator here. And when I was doing MIT challenge problems, typically I wasn't actually calculating. It was all just like, you know, find A and B. But I think for this class, there was a lot of like getting the physical intuition of the scale right. And so I switched to doing them just order of magnitude rough calculations because I didn't want to actually compute it by hand. And I mean, we were roughly on the right track for most of them, although I think I made one mistake here with one of the more complicated questions. All right, this one here, the double slit diffraction. I feel like this is from 803. There might be a chance that I have some coverage of this in my 802 notes, but I don't know whether we derived it to figure out why it's like this. I tried to do it with trigonometry and ended up with a quadratic equation, which is probably not right because the actual solution is just this d sine theta super simple thing. So this might be also something I want to go back on. Definitely a lot to learn. Definitely not, you know, we're not ready yet, but that's good, right? Like if I was just getting it super easily, then, you know, why even take the class, right? Like if it's super easy, super trivial, then it's not as exciting either. Now, I've been putting in quite a few hours more than I said that I was going to do. So this session, I'm looking at my live stream, I've been on for 3.5 hours, although a little bit that sort of preamble and debriefing. But, you know, I think I'm feeling okay. I feel like my algebra and basic sort of keeping track of arithmetic and not making mistakes with that is not where I'd like it to be. So I haven't done that much practice lately, and it's showing. But I'm hoping that by the time I get to the end of this class, I'm not going to be making as many stupid mistakes. And at the very least, I'm just going to have to be careful. I'm just going to have to go slow, work through these problems. Again, at the end of the day, my goal wasn't to get really, really good at algebra. I don't use it that much in my regular life, although it's good to know how to do it. But like having mastery and doing these really complicated things is not really my goal. My goal is more to get an overall conceptual understanding. So things I really like is I like the dimensional analysis, because the dimensional analysis is, you know, is this even plausible? Like what will be like the guesstimate of this thing? So I did like that. I'm not good at that either, but I think that's something that I want to work on more. So this is pretty good. I mean, we're rounding off day 3. I would say definitely tomorrow, almost certainly definitely Friday as well, we're going to be working on problem sets. If they're going the way the problem set 1 is going, where I'm checking every question, we might need to do more backup material. I don't know whether I want to move forward into the other lectures if I'm having this much difficulty, but we'll work on it. 2 more days, I think, should be okay. I'm hoping, I got my fingers crossed, that when we get into the later problem sets, it's going to lean more on stuff that we covered in this class, and it's going to be fresher, and I'm going to be doing it better. Although who knows, right? So we'll just sort of see. I think I'm going to spend definitely the next 2 days working through these problem sets. If there's time and I've gone through these problem sets, especially if I'm getting feedback and I don't feel like I really got it, but I did look at the answers, then we might do some Feynman techniques. We might do a little bit of, you know, cover it up, see if I can answer it, that kind of thing. We do have midterm exams. So if I felt like I didn't really get a good evaluation of my ability doing these problem sets, I might do the midterm exams. I'm doing this MIT challenge style, and the MIT challenge style was where the final exam, in a class like this, a final exam was the only thing that like counted for my overall grade. And the reason for that was just because you kind of need the feedback. You know, in an actual MIT situation, maybe you could go talk to a teacher when you're working on a problem set because you can't get something. You can talk to a peer. I'm on my own here. So if I'm not getting it, it doesn't really make sense to just bang my head for 2 hours like I would have been. Oh, I don't have the right formula. Oh, okay. So I do it on the final exam. So the midterms, I think, are also going to be an evaluation mechanism, but it might be better to do them in an exam style, so that if I feel like I learned it, but maybe if you give me slightly different questions, I won't be able to answer them anymore. That's the reason to use them like that. I only have the one final exam though, so I do really want to be prepared when I get to that evaluation stage, because if I don't do super well in it, or there's some horrible part I'm missing, not much I can do. I don't have another one that doesn't have solutions. Maybe I can do one without solutions, but I don't know how valid that's going to be. I don't know how useful that's going to be. So all said and done, I think we're doing okay. I think the stuff that I'm struggling with is mostly 803 stuff that I didn't cover, or it's, like I'm looking through this textbook to find the physical constants. I think one thing I should do is just get all the physical constants, write them down on some cheat sheet, write down some formulas on the cheat sheet. So I'm not trying to look it up in this Ohanian physics textbook that I used 8 years ago to try to find it. So that's going to be it for today. I mean, we're now getting to the meat of it. I'm excited. I know that these are sometimes difficult problems. I know that I'm not always answering them well. I know that there were some people in the comments who were doing better than me and getting the right answers on some of them, and I wasn't getting the right answers. So, choose your own pace. I think that for some people, what I'm doing here, the classes I'm following, the lectures I'm following, are just going completely over their head, and they can only appreciate it at a kind of abstract level, what's happening. And then there's other people who have mastered this, and they're like, come on, Scott, the answer is this. It should be so obvious. So I don't know in which situation that you are in watching this, but the whole point of this is to just, for me to tackle something that's challenging for me, that is, this is again going much further into the type of math that I did during the MIT challenge, much further into the physics. I always found the physics classes hard. I always found the calculus classes hard, usually because I like to make mistakes like this. I can be careless about it. So this is a fun challenge, and that's why I'm interested in doing it. So I'm going to start up again tomorrow. We'll be back at it. I don't know whether I'm going to be doing this much. I'm looking at the time here. I did 3 hours and 40 minutes in this session, and I know I did more than 3 before, which is kind of over what I was hoping for. I was hoping to do 6 a day. But I don't mind doing a little bit more in the beginning, just because I want to feel more confident with it. Feel like I've made more progress, and then if I want to ease back and just do the 3 hours, or just do a little bit less, also things come up in your life, right? Like, good reason to do more when you have more time in the beginning is because I might have some work commitment, some personal commitment that I can't do it this day. I might get sick, so that's another reason to do it top heavy like this. It's a little different when I'm live streaming because I like to keep a schedule, but when I was doing the MIT challenge, I was doing way more than this every day. So 7 hours feels pretty light, because I remember doing about probably about 10 or 11 in the first ones every single day. So okay, so we're good for today. We're going to take a pause right now, come back, finish the question that I'm working on here, and then go forward into finish problem set 1. We're almost done problem set 1, at least for the parts that we've haven't put a bookmark in because we couldn't finish. And I think I'd like to just move on to problem set 2. I don't think I'm going to touch that classical decomposition problem, because I don't really want to look at the solution yet. And I don't want to just sort of give up and just, no, this is what the answer is. And so I think I'm going to go on to problem set 2, 3, 4, maybe 5. Work through those, see how those feel compared to this one, see what my weaknesses in math are. I feel like my weaknesses are going to be more math than conceptual, so it might just be that I got to drill down some more basic stuff, but we'll see. So thank you for following. I don't know how many people are going to be watching me throughout this project, but in the chance that you are listening right now, I appreciate it. Thank you.